In Chapter 7, we're going to learn about correlations. In this particular section, we're going to introduce correlations and compute correlation coefficients. So we will be focusing on Section 7.1. Let's jump right in. Let's talk about different types of correlations. First of all, we're going to be focusing on correlations that we can compute between quantitative variables. When two variables are correlated, there's a somewhat predictable relationship between them, and we're going to compute this correlation coefficient. It'll have an R as its symbol. And what it will tell us is the strength of the relationship and the direction of the relationship. And you'll see what I mean in just a second here. If we have a positive correlation between the two variables, then the correlation coefficient that we compute will be positive. Coefficient just means number. We're going to compute a correlation value. Positive, it means that the two variables tend to move in the same direction at the same time. As one increases in value, the other tends to increase in value, which is the same thing as saying is when one variable decreases in value, the other variable tends to decrease in value. So let me give you an example of two things that would be positively correlated. High school GPA and college GPA tend to be positively correlated. Students who have very high GPAs in high school tend to have high GPAs in college. Students who have lower GPAs in high school tend to have lower GPAs in college. So I think you can see from that example that the two variables tend to move in the same direction at the same time. That would be a positive correlation. Now, a negative correlation would produce a negative correlation coefficient. So this value R would be negative when the two variables tend to move in opposite directions. So they're somewhat antagonistic. As one variable increases in value, the other variable tends to decrease in value. So here would be an example of two variables that are likely to have a negative correlation. A person's GPA, grade point average, and the amount of time that they spend partying. So let's look at that and see how that works. As the amount of time that a person spends partying increases, their GPA tends to decrease. You see how those two variables are working antagonistically. Now let's think about the flip side of that. If a person spends very little time partying, then their GPA tends to be higher. So there tends to be an antagonistic relationship there. Now, of course, we could compute a correlation coefficient, this R value, and find a value of 0 or very close to 0. That would imply no correlation or no relationship. And at that point, it's essentially impossible to predict one variable from the other. So you want to look at correlation in terms of predictive value, because if two variables are correlated, if there is some type of predictable relationship, then I can predict one value from the other variable. That's pretty much what I'm saying right over here. Now, we said that the correlation coefficient will be able to help us understand the strength of the relationship between the two variables and the direction. Here we just talked about the direction of the relationship, whether it's positive or negative. Let's talk about the strength of the relationship now. The correlation coefficient that we compute, this R value, when there's no relationship at all, we'll have a correlation of 0. That's relatively rare, though. Things are usually correlated at least in some way. If we have a positive correlation, the correlation coefficient, of course, will be on this end of the continuum. It would be a positive value. If we have a negative correlation between the two variables, then the correlation coefficient will be on this end of the continuum, negative correlations. These correlations, -1 and 1, represent the strongest correlations that exist. And like I mentioned, a correlation of 0 represents no relationship. So if we have a correlation of +1, let me just kind of write that down so we can pick it apart. If R equals 1, there's really a couple pieces of information in there. First of all, we see a positive value, so we know we have a positive correlation. And we also know it's a very strong correlation because we have a correlation of 1. If I have a correlation of R equals -0.38, I know that I have a negative correlation because that value is negative. And when I'm trying to determine how strong it is, I can see that 0.38 is a relatively modest correlation. It's not nearly as strong as what a correlation of -1 would be. So one way you might want to see it is just look at the positive or negative value of the correlation to determine if we have a positive or negative correlation, so that you can see the direction of the relationship and how the variables are related. Then just look at the absolute value of the number to see how strong it is. As that number approaches 0, it's a very weak or no relationship. And as that value approaches 1 or -1, then we realize it's a very strong relationship. So here are just two more examples, and this is always a great exam question. I say, of these two values, of these two correlation coefficients, which two represents the stronger relationship? And in this particular case, you can probably see that -0.83 represents the stronger relationship because 0.83 is closer to one of these extreme values, closer to 1. Again, I was mentioning you might want to just look at it as its absolute value. 0.83 is obviously larger than 0.64, or you can just see it with this in mind. -0.83 would be somewhere out here on this continuum. 0.64 would be somewhere out here. We can see that this is a stronger relationship. So a correlation of -1 and 1, the strongest relationships that exist. A correlation of 0, the weakest relationship that could exist. All right, so we're just trying to get a basic sense of how these correlation coefficients work. Let's again just make sure that we understand how things work in terms of the positive or negative nature. You should be able to essentially predict, at least with some variables, if you'd find a positive or a negative correlation. Let's go through a couple examples. In the first example, we're looking at alcohol consumption and manual dexterity. So that's like, your ability to use your hands, hand-eye coordination, things like that, kind of like driving a car. So we can see here, the more we take in alcohol, I'm assuming here the less manual dexterity we're going to have. So the more we drink, the less we're able to drive a car, for example. You can see that that's going to be a negative correlation. And the flip side of that works as well. So the less we drink, the more we're able to drive a car and have good manual dexterity. So that would be a negative correlation. Let's look at this next one. Calories per day that you take in and one's body weight. In general, we would find a positive correlation there. The more calories you take in per day, the higher your body weight tends to be. The fewer calories you take in per day, the lower your body weight tends to be. Let's look at this example right here. Age of car and value of car. So let's just kind of work it out in our heads. The older a car is, the less its value tends to be. So the younger a car is, the higher its value tends to be. So there we would see a negative correlation. What about this one right here? Shoe size and IQ. So again, we just try to kind of work it out in our heads. The bigger someone's shoe size, the higher their shoe size. Is there any really good way that we can predict their IQ? I'm not seeing that. People with small feet have higher IQs, lower IQs. You see, in this case, there isn't a trend in those values. We're not seeing some predictable relationship. It does not seem to hold true that people with big feet have high IQs and low feet have low IQs. There's not a predictable relationship, so it's likely there that the correlation would be 0 or very close to 0. No relationship. Let's see if we can just interpret the following relationships as well. Just trying to get our feet wet here, understanding how correlations work. So there's a positive correlation between the amount of smoking and the likelihood of cancer. What does that mean? Well, if there's a positive correlation, it means that two variables tend to work in the same direction at the same time. So as smoking increases, so does the likelihood of cancer. All right, so as smoking decreases, so does the likelihood of cancer. So people who smoke a lot have a higher likelihood of cancer. People who smoke a little or none tend to have a lower likelihood of cancer. What about this? There's a negative correlation between the price of milk and the demand for milk. So it's a negative correlation. So if the price of milk rises, what happens to the demand for milk? It goes down. We can see the flip side of that. As the price for milk goes down, what happens to the demand for milk? It goes up. All right, so we're just trying to get a little bit of practice here interpreting correlations. There is no correlation between one's salary and one's level of happiness. What we're saying here is, I can't predict your level of happiness by knowing your salary. If there's no relationship, there is no predictable trend involved, so I cannot predict your happiness from your salary. Now again, let's think about it in terms of the strength of the relationship. Let's say I said, interpret the following. There's a strong positive correlation between smoking and the likelihood of cancer. That means I'm able to predict quite well the likelihood of cancer based on knowing how much you smoke. And those who smoke a lot, they have a much greater likelihood of cancer than those who smoke not at all. There's a strong relationship, quite a bit of predictive ability there. Now let's say there's just a weak relationship. So we already know that it's a positive correlation. So let's say it's a weak relationship. It's something, not too far away from zero. Well, again, I can still predict someone's cancer from knowing how much they smoke. Not of course for every individual person. We're talking about on average, people who smoke have a higher likelihood of getting cancer. But if there's a weak relationship, there's not as big of a distinction between those who smoke a lot and those who smoke not at all. So there is indeed still that positive correlation, but the predictive link is weaker. And we can go through the same type of examples over here, and you can spend some time thinking about those on your own. All right, let's move along here with our discussion. As we compute correlations and as we think about predictive ability, one thing we'll look at are these scatter plots. These scatter plots allow us to see the relationship before we actually need to compute anything. So here's an example. Here's a bunch of numbers, a bunch of data, and in your textbook they use that data to compute some correlations and to demonstrate some scatter plots. So here we're just looking at different diamonds, and they're numbered. And they've been sorted here based on their weight in carats. You can see the weight keeps increasing. So again, here are their diamond numbers. Here's how much they're worth. And here we have some basic characteristics of the diamonds, like depth. I don't even know what table represents. The color, the clarity. So in this particular instance, we create a scatter plot in which we can see, we essentially triangulate where each diamond would fall based on two different variables. Every scatter plot involves two different variables. So one variable, here we have on this x-axis, is plotted based on the diamond's weight. On the y-axis here, we have plotted its price, its value in dollars. So here's just one example, diamond number 10. So diamond number 10 is worth $3,670. And it has a weight of 1.11 carats. So we can see this spot right here identifies where it is based on these two variables. And we do that for every other diamond. So this diamond right here weighs about 1 carat, and it's worth about nearly $10,000. We can do that with every single one of these diamonds, and that's what's been done here. And you can start to see a trend. You can see here that these diamonds in here, they don't weigh all that much relative to the others, and they're not worth all that much compared to the others. Look at these diamonds in here. These diamonds in here weigh quite a bit, and they're worth quite a bit. So we're already starting to see the pattern of the relationship here between the two variables, weight and value, price. All right, well, scatter plots are really very helpful. Let's look at some scatter plots, and we'll be able to estimate the strength and the direction of the relationship. And again, you can see here, we're seeing a positive correlation because as these weights increase, we can see that these weights are increasing. We can also see that at the same time, the price is increasing. So as weights are increasing, price is increasing. So by just looking at this scatter plot, I'm seeing a positive correlation. And I'm actually seeing a relatively strong positive correlation. Let's look at a couple examples so that you can better detect what I'm able to detect. So, for example, let's start here with a correlation of 0, what would be represented in this scatter plot. Do you notice how there's no trend here? I'm not seeing any predictable trend. It almost looks like a gunshot blast. There's simply random dots on this trend line. That would represent a correlation of 0. If we don't see any type of pattern, there's no relationship. So if we were to correlate these variables, actually give them values like the weight of the diamond and the value of the diamond, we'd probably find a correlation of 0. Well, let's look at some other examples where we really have some type of relationship. So here we have plotted, again, two different variables, and this would be a positive correlation. And the reason why I know it's a positive correlation is because it's difficult to see if you follow the trend, I'm going to do my best to kind of make a trend line in here. If you follow this trend line, we can see that it is heading up a little bit. This data is kind of heading up a little bit, and that's the hallmark of a positive correlation. But do you see how these individual data points are not necessarily conforming really well to that trend line? So it's a relatively weak relationship. Now, you'll better understand what that means when you start looking at how that changes as the relationship gets stronger. So for example, right over here, we have another positive correlation. Again, you see that trend line is much more easy to determine now. Now it's unmistakable. This is an upward trend. And we can see also that these individual data points are much better at conforming to that trend line. They're essentially tighterly, that's not a word, is it? More tightly wrapped around this trend line. So here we have a much stronger correlation coefficient. We're starting to approach 1. We have a correlation of positive 0.7. And now, of course, look at the strongest correlation possible. Here we see a perfect trend line. Again, starting from the lower left going to the upper right is the hallmark of all of these positive correlations. And because these values are completely adapting to that trend line, they're completely on that trend line, we have a perfect correlation, a correlation of 1. So I have much better predictive ability with this trend line. If I know the value of a variable, I know the value of the other variable is what happens when I have a correlation of 1. I have perfect predictive ability. We'll talk more about that later. Again, we're just trying to assess the strength of the relationship right here. We can look at the exact same type of thing with negative correlations. Although it's kind of hard to discern right over here, this trend line is negative. We can see that these individual data points do not conform to the trend line very well. So we have a negative correlation that's relatively weak. In this particular case, again, there's clearly now we can see a negative trend line, and these data points better conform to that trend line. So we have less variability from that trend. We have a stronger correlation. We're approaching -1. And here again would be a perfect negative correlation of -1. These data points conform perfectly to this trend line, and that would give me perfect predictive ability. Once I know a value for one variable, I know exactly what would be the value of the other variable. So again, we'll talk more about that predictive nature of correlations later on. But as the correlation becomes stronger, we can better predict one variable from the other. Now, not all relationships are going to be linear. So let's talk about nonlinear relationships. In general, when we deal with correlations, we are talking about linear relationships. In other words, they form a line. Look back at what we were looking at. We're trying to fit a line to our data. We keep trying to fit a line to our data. So that's what I mean by a linear relationship. Well, not all relationships are linear. Let's talk about a nonlinear relationship. So at first, the relationship between these two variables seems to be linear. This is the relationship between taste and the amount of pepper in my sauce that I like, in my spaghetti sauce. And I like pepper in my spaghetti sauce. And it seems like we're showing here that the more pepper we put in the sauce, so the more pepper we put in the sauce, this is a lot of pepper, this would be a little pepper. We're just trying to see where it falls on this particular axis. A lot of pepper, a little pepper. The more pepper we put in, the more I seem to like it. Because when there's a lot of pepper, my taste rating is higher. When there's a little pepper, my taste rating is lower. However, if we were to look at more data, we would actually see a curvilinear relationship. Because once you start putting in too much pepper, now my taste ratings start going down. Do you see how it's much tougher to show some type of linear relationship here? The relationship is not linear. The relationship is curvilinear. So this is a much more complex relationship. The correlation that we're going to compute doesn't capture this type of relationship very well. I just want you to be aware that not all relationships are linear. And what we're learning, basic linear correlation through a Pearson correlation, tries to capture the linear relationship. All right, so we just have that little caveat out of the way. With that out of the way, let's talk about computing correlation coefficients. So just to go back a step, let's talk about how we're going to compute these values, these correlation coefficients, which are trying to capture this linear relationship between two variables. Let's talk about how we can compute that. All right, well, that's next. So we're going to use this example. This is an example between high school and college GPA. And for each person, here's person A, I have their high school GPA and their college GPA. So for each person, we have two different variables measured. We're going to use a formula that I think you're going to like better than the formula that's listed in our textbook. We're going to use one that I just think is simply easier to compute, and it's based on formulas that we've used in the past. You might remember that we computed sum of squares. Well, in this formula, we're going to compute sum of squares for one variable, which we'll call x, and sum of squares for another variable that we'll call y. I mean, we have two variables here, right? High school GPA, college GPA. Well, one's going to be x, one's going to be y. It doesn't even matter which one is which. But sum of squares is nothing new, so that's good news for us. We're familiar with computing this. And we're going to use the formulas that we talked about previously in class, the computational formulas for computing sum of squares, because it's easier to compute using those formulas. That's why I want us to focus on this particular formula instead of the one that's in the textbook. The only new thing here is this one term in our numerator, which is denoted here with an SP. It's the sum of the products of the deviation scores. And it's very similar to a sum of squares. In fact, let's look at the sum of squares for one variable that we would call y. We see the sum of y squared minus the sum of y, that quantity squared, divided by n. That's the exact same thing as the sum of squares for the x variable, except we're sticking in x's instead of the y's. And the sum of the products of the deviations formula is nearly identical to these two. Instead of the sum of x squared, we have the sum of x times y. Instead of the sum of x, that quantity squared, which is just the sum of x times the sum of x, we have the sum of x times the sum of y. We divide by n, we divide by n, we divide by n. So they're all really very similar. And once we nail one, you'll see that we'll do pretty well at nailing the others. So there's some work that we need to compute, but it's not difficult work, and in general, it's not work that we've done before. So let's go through an example. Let's actually compute a Pearson correlation. And we will use this data. Let's move on to the next page where we have a little bit more room. I've given myself here a little bit of room so I can compute the necessary information that I need. All I need to do is look at the formulas to see what I need. So for example, here I'm being asked to sum up the x's times the y's. So I'm going to create a column where I have x's times y's, and I'm just labeling that. Here it says I need to compute the sum of x. Well, here is my x data, and here I've already summed up all the x data points. Let's continue to see what I need. I need the sum of y. Well, here's my column labeled y. I've already summed those up. I'm going to need to know n. Well, in this case, I have 1, 2, 3, 4, 5, 6 different people that I measured. So I'll just write off to the side that n equals 6. Here I need the sum of x squared. Well, I might as well create a column for squared x variables. I'm going to need the sum of y squared, so we'll create a column for squared y variables. And everything else I think right now is set up. So let's just go ahead and find what we need. And this is the way it's going to work. We'll simply find each one of these values using these formulas. Once we find these values, we'll stick it into this overall formula. So first let's find everything we need. We're going to have to square each one of these x values. So we have 1 squared is 1, 1.5 squared is 2.25, 2 squared is 4, 3 squared is 9, 3 squared again is 9, 4 squared is 16. All right, if we take the time to add that up, we're going to find that it equals 41.25. Let's do the same thing with y, because we need y squared. 1.5 squared is 2.25. 2 squared is 4. 2 squared again is 4. 3 squared is 9. 3.5 squared is 12.25. Again, 12.25. And if we took the time to add this up, we would find that it equals 43.75. Next thing we need here, we need xy. That means x's times their corresponding y's. 1 times 1.5 equals 1.5. 1.5 times 2 equals 3. 2 times 2 equals 4. 3 times 3 equals 9. 3 times 3.5 equals 10.5. And 4 times 3.5 equals 14. If we add all these up, we will find a sum of 42. So we just computed all of the sums that we need in here. Every place where we see a sigma, we need a sum. And now we have all of those sums computed. So now we can go through these formulas. We're going to compute each formula, as I mentioned, find each value, these three values, and then plug them into this formula. So let's go ahead and work it out. Sum of x times y equals 42. We need to subtract the sum of x times the sum of y. The sum of x equals 14.5. We will put that in parentheses just to show multiplication. We want to multiply that by the sum of y, 15.5. And then divide that by our n, which equals 6. So let's just simplify and solve that. We're left with 42 minus, let's pull out our calculator here and help ourselves out. We need 14.5 multiplied by 15.5. That equals 224.75. We're going to take the take this and divide it by 6. So divided by 6, and that equals 37.458, which we'll round to 37.46. Okay, 37.46. So let's just do the subtraction there now. 42 minus 37.46 equals 4.54. 4.54. All right, let's go ahead and compute sum of squares x. So we're going to take the sum of x squared. Here are x squares, there's the sum. That equals 41.25. So we take 41.25, then we subtract the sum of x, that quantity squared. So that's 14.5 squared. We need to square that and divide by our n, which equals 6. Let's simplify and solve that. 41.25 minus, let's figure out this fraction. We're going to take 14.5 and square it. So I'm going to multiply by 14.5. That equals 210.25. Let's go ahead and divide by 6. Divided by 6 equals 35.04. So we'll now subtract 35.04. Let's figure out what that is. 41.25 minus 35.04, that equals 6.21. Okay, so we have 6.21. So nothing real tough, we just have to go through the work. Let's find the sum of squares for the y variable, and again, it doesn't matter which variable we listed as x and which variable we listed as y. So we take the sum of y squared, that's this column right here, that equals 43.75. We're going to subtract the sum of y squared, the sum of y, that quantity squared. Here's the sum of y. We need 15.5, that quantity squared, divided by n, which equals 6. So let's go ahead and work that out. We will be left with 43.75 minus this fraction. Let's work on that next. We'll use our calculator to make it easier. 15.5, we're going to square it, so I'm going to multiply by 15.5. That equals 240.25. I'm going to now divide by 6. So I divide by 6. That equals 40.041. We'll just call it 40.04. 40.04. Now we'll just simply do the subtraction there. We're left with 43.75 minus 40.04, and that equals 3.71. All right, 3.71. Now we have all these three values that we need for this equation. So let's go ahead and compute our R value. So the sum of the products equals 4.54. That's in our numerator. We're going to divide by the sum of squares x, 6.21, multiplied by the sum of squares y. When they're listed together just like that right next to each other, it means multiplication. I'm going to use these parentheses to represent multiplication as well, just so our numbers aren't running into each other. Sum of squares y equals 3.71. And then in here we have a radical sign as well. So we need to take the square root of all of that. All right, so it just requires a little bit of work. No big deal. We have our calculators. 4.54. Let's figure out what is all underneath here. So let's go ahead and use our calculator. We're going to take 6.21 and then multiply by 3.71. That equals 23.039. We'll call that 23.04. So right here now we need the square root of 23.04. So again, let's take our next step. 4.54 divided by, let's figure out what that square root is. So we kind of round as we go just so everybody can see one step at a time. So let's find the square root of 23.04. So I put in 23.04 and I click my little square root key. That equals 4.8. So we're going to divide this by 4.8. All right, finally, let's see what that equals. 4.54 divided by 4.8 equals 0.945. We'll just call that 0.95. So this correlation has a coefficient, correlation value equal to 0.95. So that is our R value. Our Pearson correlation coefficient equals 0.95. Now let's make sense of that for a second. This was the correlation between high school and college GPA. So the correlation coefficient should tell us something about the direction of that relationship, whether it's positive or negative. Here we can clearly see it's positive. And the strength of the relationship, that value is very close to 1. So it's a very strong positive correlation. So we can predict college GPA pretty well from high school GPA if the correlation is indeed this strong. In reality, it's not quite that strong. It's much more modest. But this is a good example of a very strong correlation coefficient. Let's learn how to hypothesis test using that 4-step procedure that we learned. And in this particular case, because we now have experience computing the correlation coefficient, I'm just going to give you that correlation coefficient value. This is the value that we just computed. And then I'm going to tell you if you should test it with an alpha level of 0.05 or 0.01, and if it should be one-tailed or two-tailed. So we'll just go through a couple of examples like this. So the same 4 steps that we learned previously will apply to computing to determine if we have statistical significance for correlation coefficients. All right, well, let's think about our hypotheses. We always have 2 competing hypotheses. Now, those hypotheses are always written in terms of population parameters. In this case, these are our population parameters. We're using that sample correlation, R, to try to learn about the population correlation. That's rho. It kind of looks like a P. It's another Greek letter. It's R-H-O, rho. And it just represents the population correlation. Remember, we're dealing with inferential statistics. We're trying to learn about population values based on sample data. Now, the null hypothesis states that there are no relationships, no differences, no effects. Well, if there's no relationship between high school and college GPA, then the population correlation should equal 0. Remember, 0 represents no relationship. If we're doing a two-tailed test here, then the alternative hypothesis is that the population correlation between high school and college GPA is something other than 0. So it might be positive, it might be negative, but it's something other than 0. Remember, two-tailed tests are really the most common type of test done, because if theoretically your results can go in either direction, you should probably be doing a two-tailed test. All right, well, in the real world at this point, we collect some evidence to see how strong that sample correlation is. Here we did collect evidence and we just analyzed it, and we saw that the sample correlation was equal to 0.95. All right, we then have to compute the probability of finding these results just by chance based on the hunch that our null hypothesis is true, based on the given information that our null hypothesis is true. So at this point, what we're essentially doing is we're looking at a distribution of all possible sample correlations. And right here in the middle, we have a sample correlation of 0. And we need to figure out where are these critical regions. These critical regions are going to mark off where there's 2.5%, because we're doing a two-tailed test. I'm taking this alpha level and dividing by 2. Those critical regions are going to show me where there's 2.5% of the most extreme sample correlations right here and right here on the negative side. And we want to determine, is our sample correlation one of these sample correlations that's very extreme, very unlikely to be found just by chance, if indeed the population correlation equals 0. So do we have a sample correlation that is likely to be found just by chance? Or do we have a sample correlation that is unlikely to be found by chance? How did we find where these critical values are? Well, we looked at a table. So let's go ahead and do that together. I have a table opened up in another presentation so that we can refer to it when necessary. Here's how we use this table. Here the alpha level is listed for one-tailed test. So that's the level of significance for a one-tailed test, and it lists these alpha levels. And here we have the level of significance for a two-tailed test, and that's what we're working on. We're working on a two-tailed test with an alpha of 0.05. Well, in this particular case, we have to compute something that's known as degrees of freedom first. And degrees of freedom, we just take the number of people who we measured and we subtract 2 in this particular case with correlations. In this example, we measured, I think it was 6 people in our sample. 6 minus 2 would be 4 degrees of freedom. So when we take 4 degrees of freedom and we find the appropriate column, the column that we're looking for is right here, a two-tailed test with an alpha of 0.05. We come down here and we see where it intersects with 4 degrees of freedom. So this table is only going to list positive values. When it's a two-tailed test, the critical region is marked off at positive 0.811 and negative 0.811. All right, let's go back to where we were. So I marked off those critical regions. Well, we can see that our sample correlation of 0.95 is clearly in this critical region. It's exactly the type of correlation that we would not expect to find just by chance. It's very unlikely to find that just by chance. So we have effectively ruled out chance as a viable explanation for our results. So if we have ruled out chance, that means we're going to rule out that null hypothesis. So let's go through our reasoning, the reasoning that's involved here. Our sample correlation of 0.95 exceeds the critical value of 0.811. So the probability of finding this result just by chance is less than 5%. Those critical regions marked off, the most extreme 5% of the cases, and our sample mean was in there. So in other words, our result is statistically significant at the 0.05 level. What that means then, of course, is that we are going to reject the null hypothesis, so we actually cross it out. And we're going to take on the alternative. We now believe that the population correlation, that is rho, the population correlation between high school and college GPA is something other than 0. Well, we have evidence that it's positive. So we conclude that the population correlation between high school and college GPA is greater than 0. In other words, it's positive. We have a positive correlation. All right, well, we found a statistically significant result. Let's just go through an example to see what it would look like when we would not have a statistically significant result with a correlation coefficient. So here again, I'm just providing us with some information. Again, let's assume we're looking at the correlation between high school and college GPA. It says a researcher randomly selected 32 people and recorded their high school and college GPAs. Let's say at this point we found that the sample correlation was equal to 0.28. So again, it's positive, but it's much more modest. Is there a significant correlation between these two variables in the population? So we're using sample data to try to learn about the population. Now our burden is a little bit more heavy. We're going to test this with an alpha of 0.01. So we're going to need more evidence to reject the null hypothesis. We'll do a two-tailed test. So our hypotheses should remain the same. The null hypothesis is that the population correlation between those two variables equals 0. The alternative is that the population correlation between those two variables does not equal 0. We're going to collect some evidence, and we already did here. I've summarized it for us. So the sample correlation equals 0.28. That's our sample evidence. We now need to compute the probability of finding these results based on our assumption that the null hypothesis is true. So based on that assumption that the null hypothesis is true, we can see here all the sample correlations that we would expect to find. So just by chance, we would expect to find sample correlations that are in here, but it's very unlikely by chance to find sample correlations in here. How did I find these critical regions? Well, I know we're using an alpha of 0.01 for a two-tailed test, and we've measured 32 people. If we've measured 32 people, that means we're going to have 30 degrees of freedom. So let's consult our table. We don't need to memorize the whole degrees of freedom thing. The table shows us how to compute it. So we have 30 degrees of freedom, we're using an alpha of 0.01 now, remember, for a two-tailed test. So we want to look at this last column all the way over here. Let's remind ourselves where 30 degrees of freedom is. So here is our critical value. It's going to be a positive and a negative 0.449. So going back to our test here, we see those critical values. We see our obtained R value of 0.28, and that's somewhere right around here, right? It's not in the critical region. So in other words, this is exactly the type of correlation that we would expect just by chance, even if the true population correlation equals 0. In other words, we don't have enough evidence now to reject that null hypothesis. We simply don't have enough evidence. So let's go through our reasoning for it. Our sample correlation of 0.28 does not exceed the critical value of 0.449. So the probability of finding this result by chance is actually greater than 1%. And we all know when we see that greater, we do not have statistically significant results. So the result is not statistically significant at the 0.01 level. We will fail to reject the null hypothesis, which in other words means we are going to retain it. We're going to keep it. We still think the population correlation equals 0. And we conclude that the population correlation between high school and college GPA is indeed equal to 0. So how do we make sense of finding this sample correlation right in here? Well, just due to chance variation, just due to basic sampling error. From one sample to the next, we'd expect to find different correlation coefficients. But over the long run, if we were to measure the entire population, we expect that we would find a correlation of 0. We simply don't have enough evidence right now to say otherwise. All right, everybody, that was a lot to take in for right now, but you've got a really good basic understanding of how to compute correlation coefficients and how to use our 4-step process to determine if they're statistically significant. That is the key content from section 7.1. The content from the other sections is much more brief. For now, that is all.